2 of the SMA Interferometry School. So the format again is going to be basically kind of just like yesterday. This morning we're going to have some more hands-on-ish type training. First with Andrew, and then later this morning with Luca, and do some special topics in the afternoon. So just a reminder for people who are joining us online, please remember to mute your mics. And speakers, also please remember to mute your mics. We should just have the one mic here, and nobody else should have their mics on. All right, so Andrew, go ahead and take it away.
All right, thank you. So good morning, everyone. We'll see how much I can keep us all awake in the early morning. Today I'll be talking about flagging and kind of an introduction to mirror. For the most part is what I'll try to focus on here for the next while. If you've got questions, feel free to interrupt me as I go along. So like I said, we're going to start out, we're going to have a little bit of a crash course, just kind of the very, very basics of mirror so that when you go to look at it later, it doesn't look like complete gibberish. And then we'll kind of go through some of the stuff we talked about yesterday and try to do a little bit of step-by-step of the calibration process as we go through. And a lot of this is accessible through both the mirror cookbook that's available online. We're done a lot of work done by Charlie Chi, as well as a lot of the stuff that's available online on the SMA assorted data reduction resources that are available. So mirror, this is the primary way that it is recommended that you calibrate your SMA data. It is a IDL-based software, so if you are comfortable with IDL, then a lot of this should come easy. If you don't, IDL is a fairly straightforward language, so I won't go too much onto the details of anything IDL specific. But it was originally developed by Nick Scoville in Caltech for a different observatory, but later got adapted by Eric Tito and is now supported by a variety of people at the SMA, where its primary purpose is for the analysis of SMA data specifically. I know at least when I first got here, I got a little confused that there is in fact a difference between myriad and mirror. They are not related whatsoever, despite the names being contained. But I figured I'd just put that there. And this is something you can see on the website where it's a recommendation of, I'm going to talk about mirror a lot here because that's what we recommend you calibrate your data with. However,
sorry, I missed that.
So did I. So the calibration is what we recommend doing it. There has been some work recently to try to do calibration in CASA. As of right now, we can't 100% approve it as we haven't fully tested it in all the scenarios. But some people have said they've done it successfully, albeit with some older versions of CASA. But all the calibration is going to be done in mirror. And then the imaging, once you get into there, we kind of recommend you do it with either Myriad or CASA. Most of the stuff we'll be talking about here will be done with CASA, as it tends to be a little bit more of the dominant software these days. Some initial caveats about mirror. You do need an IDL license. So if your facility doesn't have one, the CFA does allow some access if you have SMA data to be able to work on it a bit. So if you have issues with that, you can contact your SMA friends to try to get access to that. You will need, like I said, additional software to actually do the imaging, but CASA and a lot of these things are pretty easy to download. So if you're comfortable with things like CASA, then that should be fine. And one big thing that I'll kind of start touching on early is the fact that it does require loading entire data sets, which can cause some memory issues. So either you got to be kind of careful with how you're storing your data or what computers you're doing, or you kind of have to jump through a couple hoops as you start analyzing your data, just because these data products can get very large. And mirror requires you to load the entire kind of chunk of data that you want to look at all at once, which can be a little frustrating at times. So to start out, we have mirror. And I always like the first thing, anytime I pick up a language, is the first thing I try to figure out is how do you actually ask it a question. So these are the different kind of help manuals that you can, as you look at these tasks as you go through, these are kind of the good ones to look at. These are kind of your more standard things that would interact well with IDL scripts. And then you have mirror help, which will help you look up any of the given tasks, such as, we'll talk about like gain cal or something like that. If you ever have issues, I mean, all this is also contained all online and is pretty well documented. But it's always good to show this up first. All right, so start out with, there's kind of two major ways before we get to do anything is you start reading in your data. Once you kind of run this read data with whatever your kind of directory that contains all your data is sitting here, you can sub-select from there using either select or dat filter command. They have slightly different syntaxes and they do it slightly different ways. I've kind of found as you kind of go through the tutorials and stuff like that, they kind of explain which ones you want to use, but you can kind of switch back and forth without too much of an issue. But a handy thing about when you have select, so basically as you read in all your data, you then can run select once you have some amount of data, and it'll display kind of everything about your observation. So if you use CASA, I always kind of think this is a little bit like list obs, but because this is IDL where you can sub-select down where you're only holding on to kind of, or selecting certain chunks of your data, you can kind of remove certain amounts. So if you only want to select and look at your science target, or if you want to only look at one of your calibrators, they'll pop up when you sub-select down. And when you just type select, it'll show you everything. This is a little bit of an older one. This is not with Swarm, I believe. So that's why the all bands look a little bit different than what you might see when you're working on stuff later this week. But this is kind of what you'd expect, which is the sources, baselines, the bands, side bands, polarizations, kind of all of it in one nice, easy to look at place. So we said that prints out the basic info. These are kind of different examples. So as you select, you can select for a variety of different parameters. So, different integrations, different bands. We'll get into what this positive weight means in a little bit. And it's very similar when you're using this DAT filter where it's resulting from stat filter, where here we're, for example, saying that the weight is greater than 0, and we're sub-selecting all the data that has positive weight. So the thing you want to kind of, as you first get your data, you get an email that says, hooray, you got your data. One of the first things you want to look at is how you're actually going to handle that data, because mirror is quite memory intensive. Typically, you require about 2 to 3 times whatever the file size you're working with. You need that kind of memory ready to go. And for Swarm, we're talking 100 gigabyte files. So it's often recommended that you do a couple of these different tricks to sub-select down that you're only loading a certain amount of the data at one time. So the first thing, you can just select only the data you need. For example, so if you're only working, for example, with one sideband, or you only want to process one at a time, when you read in the data, you just do, for example, the lower sideband. You look at one receiver, maybe only a certain number of integrations, bands, etc. Another thing you can do is once you load your data with read data, Mirror has these different mirror save and also a mirror restore as well, where you can kind of save whatever you're working on. So as you're working through maybe calibrating some of your data, you can save it using mirror save, kind of whatever you're working on, and mirror restore and pull it back up. So you don't have to kind of repeat the whole process as you're going along. So that'll save you a bunch of time. And the other big thing is this SMA rechunker, which is a script that'll basically rebin your data down. So if you feel like you don't need necessarily to achieve your science goals, you don't need all the spectral resolution that you have, you can run this SMA rechunker. And this is not like a mirror script like most of the other things we'll be looking at. This is actually just, it's its own script that you just run normally in the terminal. Here's a link to download it. This is also available on, if you look up on the website, you can also find it right here pretty easily. But it's fairly straightforward, where you just give it, whatever your original data file is, it'll rebin it into a new file and some rebin factor. Often we see somewhere between factors of 2 and 8, depending on what kind of science you want to do. But if you can't necessarily rechunk your data for whatever reason, you have to kind of be careful with how you're sub-selecting things down. A big thing as we're going through, we're going to be flagging a bunch of data. So we have kind of two main ways you flag things in Mir. You have just kind of the brute force way on the command line, which is the command flag. And so what you do is you load in some amount of data. So for example, here, if I want to flag all the eye pointing data, it has a little tag here called pointing. And so you can just flag all that. I realize there's a Q there for no good reason. You can also do it similar. For example, if there's a bad antenna, you can just say this is kind of the variable for antenna here. So you just say for any antenna that has 4, you flag it that way. Similar for sources. You can do it for things like TSIS as well. So this is kind of a nice flexible way as you're looking through your data. Maybe you're pulling up different plots and you're like, okay, it seems like this one's not good. This is kind of the easy way you flag it. You also unflag it with the exact same command, which is pretty handy. And the other way you do it is as you're pulling up your continuum and spectra plots, you kind of can do it on a more GUI based clicking by hand on specific points, but I'll get to that in a little bit. You can also look at statistics pretty easily. I know Cardo was just talking about error recognition. If you just kind of want to have a quick look as you're going through your data, there's kind of a set of pretty standard deviation, mean, median. I think there's some other ones in there, but these are the ones I just knew about. So if you want to just get some quick stats, these are some easy ways to go about it. All right, so let's actually start kind of stepping our way through this kind of calibration pipeline, you can call it that. You start out, one of the first things you do, a couple times a night, we do these pointing corrections, typically somewhere between 1 and 3 times in your data set. You'll have just kind of these gaps from your science where you went off and we had to do some pointing routine to make sure that we were pointing at the right source. They don't really have any good scientific output for us, so you can just kind of flag them out, which is pretty straightforward first step. If you have any sort of older data, I would say the past few years ago, what they kind of suggested you did, instead of having this pointing flag, you just did it by how long the integration time was, because the shortest integration times were always the pointing scans. Unfortunately, or I guess fortunately, because we can do much shorter integrations for science, this is no longer an easy way to just call out that chunk of data. So now we introduce this flag in there, so we can check that. So the next thing you want to do is you want to inspect the data visually and perform some additional flaggings as needed. So I had mentioned you have these kind of different plotting functions. You have plot continuum, plot spectrum, and plot var. So plot continuum, this is what appears to be a very blurry version of what you pull up when you do a plot continuum. So you may remember seeing some of these pictures yesterday, where you have your amplitude and your phase. And you have it for a variety of different baselines and different, your upper and lower sidebands or something. And then you can see there's different colors depending on what different targets you were looking at. And you can see you have this periodic, so this was likely you're going between your science and your gain calibrator. This is probably your flux calibrator up here. And this was probably like a BANDPASS right over here. When you're looking at your plot continuum, when you run this, you can plot it versus integration time or integration along or hours, and you can plot it versus just amplitude, just phase, or both. And then once you do that, you show a little menu will pop up with your mouse, and if you you can left click to zoom, right click to scroll through it, and you middle click to bring up a bunch of different menus. Some of them are simple as exiting, but others, there's an F1, and that'll actually allow you to, as you pull it up, to flag the data as you go along. So you can actually click on individual data points and flag them, and it'll produce a nice little X on it, and allow you to flag your data in a way that's a little bit easier this way than actually trying to type it all in by hand and figuring out exactly what integration is. So as you're going through for your continuum and flagging, you want to make sure you have good data on a strong calibrator, and that should show up as a small phase and amplitude scatters. So everything should be nice and tight with no real, sharp temporal variations. So that's kind of one you will want to look for in this one. Then we have a similar one for plot spectrum. A lot of the syntax in terms of the flagging and stuff like that I mentioned is pretty similar to this one. Another thing you want to make sure you do is, because the noise gets very high on the edges of your chunks, what we tend to do is we normally trim somewhere between about 8 to 10% of the data that in these. So you can see them here. You can see there's little black gaps between all of these. So that's just something, if you want to make sure you have absolute perfect coverage that's completely continuous, you want to make sure you set up your windows that they'll actually have a little bit of overlap. Otherwise, you will have these little bit of gaps. And it's just a good thing to know because they tend to be pretty high, pretty noisy on the edges. And a quick way to do just to plot that, you can see is just plot spectrum. You can color by the band. And you just say N-trim 320. So that's the 320 channels on either end. When you do this, it's a good idea to also keep in track of, okay, well, you'll take the however many, you'll maybe say, oh, I have X number of channels, and I'm going to take 8% of them. You want to make sure you know if that's the number of channels you have before or after you rechunked, because if you do that, you might accidentally clip way too much. So as you're doing this, you want to check for a good signal to noise at all your different baselines, or if you have a bad spectral band, you want to see if you have any of these weird ones where it's 0 in phase and amplitude all over. You can see there's these little spikes here, which we'll kind of look at in a bit. And then you have plot var, which allow you to plot a bunch of different things against one another. So if we're trying to do this error recognition that Carter was talking about, we have things here. So you can plot amplitude versus elevation, amplitude versus hour angle, projected baseline. Here's just kind of a bunch of different examples of plotting X versus Y's and some different, you can, for all these ones, you can color by different things. You can set them in different frames, like what the different frames will pop up as. So this one, it's doing different antennas and inside bands. But these are ones you'll also want to, as we're going through, check for anything weird that's popping out. And Carlo kind of went into that in a good amount of detail as well. Next thing you want to do on the checklist is you want to look for these spikes. You can kind of see them here on this one. You can see this really bright green spike over here. You can also see some spikes over here in the green over here. So you can kind of inspect them by eye. If you want, you can kind of flag them by hand that way. Another way you can do it if you want to try to fix them is there's this routine here in Mir called UTI check spike, which will go through and automatically detect and optimally try to fix the spikes as best as it can. So here, for example, we do it on one of our calibrators, and we did that N-trim 320 again. And if you wanted to try to fix it, use the /fix. Otherwise, it'll just kind of check to see if there are spikes. In terms of the optimization, depending on what the case is, it might be more efficient for you to just kind of do it by hand. For example, it's a little hard to see here, but you can see this spike got checked and found and fixed, but you can see it's actually still there for them. It's not as bright, but it's still there. So you probably have to either try to fix it again or try to look at it a little bit more detail of what's going on. If you can also want to try to, instead of having this find the spikes and then fix them by hand, you can also do this using the UTI cham fix. So if you zoom in, so that's what this is here, and there's a little spike here. If you zoom in and you can actually determine that this is channel 991, you can then run UTI cham fix on 991, it'll fix it. And the rough way it does it is basically it looks at a few of the channels around it, and it tries to find an average value that would be kind of consistent with a smooth feature going across here, instead of whatever the spike we're seeing here is. All right, so next we're gonna apply TSIS, as was talked about yesterday. So TSIS is measured continuously throughout the as we're looking at all the different antennas. And the important part about applying TSIS is it allows us to rescale from a raw amplitude to an actual brightness temperature. So some sort of Jansky-esque unit. And it also allows us to actually simultaneously, in certain cases, correct for broad changes when you have the amplitude over time. So if you have large slopes, then you're kind of always keeping an eye on your TSIS, whether it's due to changing in elevation, maybe the weather changed kind of rapidly, but not too rapidly. You might be able to correct that with the TSIS application as well. So the first thing you gotta do is you do the plot var and try to see if there's any bad TSIS values as you're looking across. If there's any weird ones, there's a nice little routine here called UTI T6 fix. It'll try its best to find kind of abnormal features that are not smoothly going across. I think, yeah. So then once the t-sys plots look fairly normal, the correction can be applied, and it's just apply t-sys. And so this is kind of a before and after. So you can see there's kind of a little bit of a moderate improvement in it. But the bigger thing is you can't really read it from here, but we go from an amplitude of being like 0.0002 to kind of reasonable flux values that we would expect for some sort of bright source that we'd be looking at. And so we run t-sys plots to try to make this look normal. And then we regenerate the continuum channel. I didn't mention this earlier, but in certain cases at the very start, you may need to generate the continuum channel if it wasn't put there in the first place. And that's just this command UTI average band. So that just takes the band that you have and averages it out to make a new channel that is just the continuum, so no spectral information. All right, up next we have the bandpass calibration. So as we mentioned, for each of the bandpass and antenna, we can compare it to a bright quasar, which is theoretically free of any major spectral features and has consistent amplitude across the covered frequency. And so because it's relatively flat across any given bandpass, we can compare the response of the antenna when it looks at this bright quasar versus whatever science target we're looking at. And so if you can think of it from an optical sense, this is kind of like taking a little bit of a flat field across your spectral window. So here we have a bright quasar that can be observed for a long time to derive the frequency dependence on the gains. And then we correct for those frequency dependences. And we can then apply that to our source. So when we're looking at this, we can apply these, and this is what you kind of get before, and this is what you kind of get after. And this is actually so this was it fitting for the bandpass. And this is kind of what you get. So when you do this, you do both a bandpass through a phase and also the amplitude. And so you can see here with these commands here, when you do Pascal for bandpass calibration, you select what the cal type is. So first one here we use phase. Second one we do here is amplitude. You can do some amount of, you have again this M trim that we talked about earlier. We have you have to set a reference antenna when you're doing these calibrations. A certain amount of smoothing that you do across the bandpass, across your calibrator. It's kind of recommended that you do. And so the kind of results you get from that are here. So this is with no bandpass calibrator done. Then we did the bandpass calibrator for the phase. And so you can see the phase goes from kind of these striping features to this nice kind of consistent phase all the way across. And then when we do the amplitude calibration after that, you can see it goes from kind of this more jagged feature to a nice consistent amplitude all the way across the bandpass. So after that, we do the gain calibrator. So here we want to kind of understand how the gain responds to the sources in the sky we're looking at. So theoretically, if we look at a point source, we should know very well how that should respond to our antenna, and we can calibrate based off that. But the changes we're having here is due to for a lot of these is the fact that we're having these atmospheric changes. So these occur on rather rapid timescales relative to things like changes in the bandpass. And so that's why we need to frequently go back to a bright source that's typically a point source to see how it's changing throughout the night, which is why when we do these observations and we go back and forth between our science target and our gain calibrator, that's why we go back and forth, is because we're measuring these atmospheric changes. We also measure the gains as function time the same way as done the bandpass, and we apply them to our target. So here, instead of Pascal, we use gain cal, and again we specify the cal type as phase. And I guess I covered over this one here, but there's just like a quote mark there. And so you set what the x-axis is, so you have x equals hours. You have some amount of smoothing again that you do. Again, you set a reference antenna, and then here again we do the gain cal, but for amplitude the next time. And again, you do a certain amount of smoothing. And from that, here we have the gain calibrator again, where we go from no calibration done here to this one doing it just purely with phase. And then this is what we get when we do it with the amplitude and the phase together. So it's a little bit easier to see in the phase, but the amplitude does actually get a little bit nicer as we go from with that calibrator there. And the last big step for the calibration that we want to do is the flux calibrator. So here, for some sort of solar system object that we look at, we should know that the flux is fairly constant. Its flux is not going to be rapidly changing, as it's just a kind of a disk. And even though we may resolve out some component of the emission, we should know how much we are resolving out pretty consistently, because we know how an interferometer of size X how much of flux it would resolve from a disk that we know very accurately the size of. And so as a result, we know the overall flux of these solar system objects fairly well. And so what we do, if we want to use this in order to determine what the overall flux values across all our different observations are. So the first thing we do is we do a calibration comparing kind of our quasars with our planet, and just to make sure we understand how bright our quasars are, because we know the brightness very well for the planets, and we can compare them back and forth. Once we do that, we can do this amplitude calibration of the quasars using the planet's flux as a reference, and then we can compare what we get. Oh yeah, here's the what you typically type in roughly for this quick calibration. So you select down your data. So you can see we picked some sources here. So these are kind of classic, some commonly used calibrators that'd be reasonable for some quasars to look at. And then Uranus or Neptune are kind of the best targets. Other ones such as Callisto tend to be pretty good for doing for being your flux calibrator. And then we do a gain cal with the phase, and then we do. So then we have the amplitude calibration. You can do. There's one command that looks very similar to this one that you do for the amplitude, but there's also just a command in Mir that's just SMA flux cal as well, and they both work pretty well. So I just gave you the kind of more easier to remember one, and then we compare these fluxes. We run this command called flux measure, and this gives you a bunch of information here about the brightnesses you got of your quasars, and then you can compare this to kind of online tables and databases of how bright these have been in the past, and make sure that everything's lining up kind of the way we would expect. And so now we have theoretically a nice, beautiful calibrated data set that would be perfectly ready for doing some imaging for. And apparently, I underestimated how fast I would talk through this, because I think that's my last slide. So we got plenty of time then. If anyone else has any questions or anything.
I have a doubt, please. I think in the step 5, one of the plots you have shown has like, after the phase calibration, you show like two, a little bit forward, I think.
This one?
Yeah, there. So why in the phase you have two lines? Shouldn't it be like all going to one phase after you calibrate?
I think that's just this is, let me make sure that's, so yeah, that's 100 minus 100. I think that's just like a mirroring effect or something like that. I think it's fine.
Two sideband.
Yeah, that's what it is. Yeah.
The lower.
I see. Okay. Yeah. But in theory, I mean, you expect in one band to everything collapse to one constant phase when you calibrate. Okay.
Yeah, so there are times when the sidebands can differentially respond to things. So like, for example, there are local oscillators that can distribute it out to all the antennas. those local oscillators end up being mixed with the sky signal. So for the lower sideband, if there was a phase drift, it goes down. For the upper sideband, it goes up. Things that are atmospheric, of course, should affect both sidebands roughly equally. But there are things that differently affect different sidebands. So in MIR, they're treated differently because they can actually have different phase solutions.
And connected with this, then could there be an ambiguity of pi or 2 pi in these phases, and what would that do to the image or the data?
Yeah, no, it can pop up.
And how you detect it? How do you know if that happened?
I don't remember.
So I think at least if there are in the frequency domain, it's pretty rare that you see
That much.
something to that extreme degree, unless something is really done wrong with the telescope. The only time that I've generally seen that, and maybe Mark, correct me if I'm speaking out of turn here, the only time I generally see that is when the atmospheric phase stability actually tends to be very poor. And the atmosphere, being a physical entity, doesn't typically turn on a dime. So you will see the phase
Gradual, yeah.
very quickly ramping up. So if you see something that looks like, things look fine, all of a sudden there's a lot wrapping.
Yeah, that's kind of more likely what you'd see is a bunch of wrapping kind of going around a couple times or once or something like that. The fact that you wouldn't have like an instantaneous jump from 0 to 2 pi or something like that, I feel like that'd be, you'd see at least some slope along the way.
And typically we do the calibration every 15-20 minutes.
Yeah.
So if within that time it doesn't change by 2 pi, then or anything, if there's no big jumps, then we'll be able to catch it.
Yeah.
But if there is, you should see like a smooth variability, like something. But unless there's some like absolute jump, in which case, let's say it's more than a few degrees, tens of degrees, then you will have potentially a phase jump, and you can go back and look at the gains like that were fitted, and then see if there are jumps in the gain, and then that's one area where you can look at the source. And when you image, you can go back and say, okay, if I leave that part out of the source, and then see if the image changes.
That also goes back to like designing your observations, what we talked about on Sunday evening. Basically, how you decide that 15-minute interval is basically you don't want the phase to like wrap around. So if the weather is really poor and you would expect the phase stability of the atmosphere to like wrap around the whole 2 pi, that would be actually very poor. Then what you want to do is you want to make you want to go more often to the calibrator so you can track that wrapping of the phase over time.
You mentioned the smoothing step. Could you just elaborate on what values you should use? Because I saw some like 0.6 and
Yeah. I'm trying to remember for which one specifically. What? What'd you say?
That's in unit of hours.
Yeah.
Yeah.
I remember.
Yeah, that's ours. Yeah, a good smoothing is like, if you have, it depends on your calibrator. So you typically do calibrator source calibrator, right? So then you can pick a smoothing which kind of overlaps so that you have a continuous phase variation.
is there like a rule of thumb to pick that value? Or?
Yeah, so it just depends on how your atmosphere is changing. Right? If your atmosphere is changing very slowly and gradually, then you don't, so your smoothing could be large. Right? But if your atmosphere is changing very fast, then you don't want too much smoothing because then you will decorrelate the phase. So I think you have to look at the data and then decide and how it is. So yeah, it's
like smoothing any function. You got to know what the overall profile is.
So you look at the data and then you decide based on how the atmosphere is changing. It's the same with like, so this is smoothing in time. So when you do gain cal, that's doing a time-based gain as a function of time. You can go back and look at the bandpass calibration, the smoothing there, so you can go back and so here the pre-averaging is done first. So, whatever, let's say you had 16,384 channels, you would average by 8. And then once you have that, then you would smooth it. And then you would smooth. In this case, there was no smoothing done, right? Smoothing is one, meant you took every single channel and after the averaging. But so you could play around with whichever works. And you might find, like, if you see you'd have to again look at the plot of the bandpass first. And you'll be able to tell from there how much is changing. So if you have too many jagged things, it may be noise. But then sometimes there are very smooth variations in bandpass, and there might be like a sudden dip in phase or something like that, or amplitude. And so you wouldn't want to smooth it. If you have signal to noise, then you don't want to smooth an average. So it's I think you have to look. So I think those plot continuum and the plot spectra are the first things you should be looking at. And I think you have to spend most of your time looking at that. And then once you have, that'll let you make the plan for how you want to do the rest.
Thank you.
So maybe one quick one. And then for the bandpass calibrator, when you go to the tool to prepare your observations, so you said you want them to be free of spectral lines and kind of flat spectrum.
Yeah.
So is a website from SMA already giving you only good
Yeah, so
sources of these, or?
Yeah, there's the SMA has a catalog of the different calibrators and their positions in the sky and how bright they are and stuff like that. Yeah, that's all on the SMA website, like Azure.
Yeah, but when you choose for the bandpass calibrator,
Yeah.
does it give you a subset that is good for that, or you have to know them?
I think most of the ones on the list are all fairly.
So on the submillimeter calibrator list, it will highlight. I think there's a highlighting for flux calibrators that are greater than 2 Janskys, with the hint that this might be a good bandpass calibrator.
Yeah.
Okay.
There are 3 in particular that are most commonly used if we can, which are 3C279, 3C 454.3, and 3C84. There are things that are of order 10 Janskys. Basically, you want to try to grab the brightest thing in the sky for your bandpass calibrator, mostly because in order to get high enough signal to noise in a small number of channels in a reasonable amount of time, you want as bright a thing as possible.
Without spectral lines.
Right, without spectral lines.
Yeah, so my question was about, we see the flux in the catalog, but I don't see if it has spectral lines or if it is flat spectrum
Those are all
across my
quasars.
band.
Yeah, they're all quasars, so they're all going to be fairly flat spectrally.
I might just add, I think that this issue may come up if you use planet or planet moon as a bandpass calibrator. So when the SMA is more compact configurations, you see enough flux even along baseline for those planets. For example, for Mars, you don't want to use it if you have CO in your tuning. But the bright quasars, they're featureless and it's safe to use with bandpass.
Thank you. And for the flux calibration, it wasn't clear for me if you are dividing the lower and upper side band and doing them individually or not.
Sorry, could you say that again?
Are you doing the lower and upper side bands individually?
Yeah, you do them all separately. Yeah. Anything else?
Can you go back to the applied thesis slide?
Overshot. This one? Yeah.
Yeah, I was just trying
Or I
to,
think I had one follow-up after that.
there might have been another one, yeah. What, is that a before and after?
Yeah, so it's not, this isn't as much of like, this looks better than the other one. And you can't read it because everything's shown up blurry on my presentation. But the big thing is you go from voltages to a actual flux value.
Correlation coefficient.
Yeah. Sorry.
Yeah, if you walk up to the screen, you can see that one is 10 to the minus 3, or 10 to the minus 4, and then the other one is in
Like
units.
yeah, this is like 10 here, and like the top of that, like the first line up there is 0.0001. So yeah, that's the big part of it, is that we actually have more useful values.